Today we are going to discuss about Cauchy-Euler homogeneous differential equations. Cauchy-Euler homogeneous differential equation is also known as a homogeneous linear differential equation, and it takes the form x raised to n d raised to n y by dx raised to n plus a1 into x raised to n minus 1 into d raised to n minus 1 y by dx raised to n minus 1 plus etc. plus a n y is equal to f of x. See where f, a1, a2, etc. a n, all these are constants, and the RHS f of x is a function of x. And you could see that the highest power of order of the differential equation is n. So this is a general differential equation of order n. We are going to deal with a second order differential equation. So the working rule, let us look into. So generally, if I speak, let me take the nth order differential equation, Cauchy-Euler differential equation. We will go for a substitution method to solve this problem. X is equal to e raised to z is taken as the substitution, and if x is e raised to z, then z can be written as log x, and you will take xd as d1, x square d square as d1 into d1 minus 1, x cube d cube as d1 into d1 minus 1 into d1 minus 2, and so on, where d1 is the differential operator d by dz, where in the beginning we have taken d, which is a differential operator with respect to x. So we can rewrite our equation in the form f of d1y is equal to fn of z, where this f1 of z is going to be the value of the function f of x in terms of z. Let us look into one problem and see how the solution can be taken out for this. So let us write the given equation in the differential operator notation as 4x square d square plus 4x d minus 1 into y is equal to 4x square, where d is d by dx. As you know, in the given equation, it is d square y by dx square. I have taken in the solution y double dash. Another second line, you could see d square. All these are different notations of this differential operators. And first order, second order derivatives. So this is a second order Cauchy-Euler equation. First step is identifying the given equation. And then we are going for a substitution. Put x is equal to e raised to z. So z is log x. Then since the equation contains only xd and x square d square, we are only taking up that xd as d1 and x square d square as d1 into d1 minus 1. As we already said, d1 is d by dz. Now, you will take all these substitutions. Wherever x comes now, you will replace with e raised to z. And wherever xd is appearing, we will replace with d1. And x square d square will replace with d1 into d1 minus 1. So that the above equation can be rewritten as 4d1 into d1 minus 1 plus 4d1 plus minus of 1 into y is equal to 4 times e raised to 2z. That again, opening the bracket, simplifying and cancelling, we are getting the equation 4d1 square minus 1 into dy is equal to 4 e raised to z. Okay, now let us think about solving the equation. So for this, since it is a homogeneous equation, non-homogeneous equation, LHS is solved based on the complementary function. RHS you have to solve by taking the particular integral, by finding the particular integral. So first let us focus on the complementary function. For that auxiliary equation, let us take the LHS expression can be written as 4m square minus 1 equal to 0. You might have seen that how we have taken the auxiliary equation, we just replaced d1 by m. Now solving the equation, since the auxiliary equation is of the form a square minus b square, applying that identity, and expressing it as a plus b into a minus b, the equation can be rewritten as 2m plus 1 into 2m minus 1 is equal to 0. So that you will get two values for m. One is minus 1 by 2 and the other is plus 1 by 2. Thus, we are getting an equation with real and distinct roots. Two real roots which are distinct. Then the complementary function can be written as c1 into e raised to the first value of m into z plus c2 into e raised to the second value of m into z, which is c1 e raised to minus z by 2 plus c2 e raised to plus z by 2. And we can replace z with log x. So it is c1 e raised to minus 1 by 2 log x plus c2 e raised to plus 1 by 2 log x. Again, e raised to 1 by log x is nothing but x. So we can rewrite the above step as c1 into divided by root x plus c2 into root x, because log of 1 by 2 log x is not log 1 by 2 times log x is nothing but log of x raised to 1 by 2. And e raised to log x raised to 1 by 2. X raised to 1 by 2 is nothing but root x. So e raised to log root x is root x itself. Similarly, the negative. So root x will appear in the denominator. Then we can find the particular integral. So when you look at the particular integral, you could see that it is a particular integral of the form e raised to function, e raised to 2z. So how do we solve the particular integral for the case e raised to 2z? We just need to replace the coefficient of z here, which is 2, where we have to replace that in the place of d1 square. So it can be written as 4 divided by 4 into 4 minus 1, which is 16 minus 1, which can be written as 1 by 15. 4 by 15 into e raised to 2z. Now expressing in terms of x, you can rewrite it as 4 by 15 into x square. Now let us find the complete solution or write the complete solution for this particular question. Complete solution is y is equal to complementary function plus particular integral, which is c1 divided by root x plus c2 root x plus 4 by 15 into x square. This is the method for finding the auxiliary equation as well as for complementary function as well as the particular integral, combining them together to get the complete solution for a homogeneous linear differential equation or Cauchy Euler equation. So this is an example of order 2, second order Cauchy Euler equation. Thank you.